All right, everyone, let's go ahead and get started. Please take out your notes. Here's where we were at the end of class last time. We have the rotational analog of the second law. Quiet down, please. The rotational analog of Newton's second law is that the net torque that's applied to the system results in an angular acceleration. How much angular acceleration occurs relies on two things: the amount of torque itself, and then also what's called the rotational inertia. The rotational inertia I is also, by the way, sometimes referred to as the moment of inertia. So if you hear the two terms, they mean the same thing. Now, for a system of point particles, as I described at the end of class last time, all rotating about the same point, the axis of rotation, the rotational inertia is the following summation. The product, first of all, of the mass of the particle with its distance from the axis of rotation squared. You then add all of that together. That then gives you the rotational inertia of the system. This is the derivation, of course, that I went through at the end of class last time. And then at the very end of class last time, I wrote down the following sentence. This becomes an integral for a distribution of matter. So what does the integral look like, and how is it calculated for a couple of symmetric distributions of matter about the axis of rotation? Well, first of all, in general, the integral looks like the following. Okay, let's say that we have some coordinate system like so, and then I've got some object. Like so. And let's specifically say that right here is the axis of rotation. So the thing is rotating in the xy plane like so, say clockwise or counterclockwise, and that is perpendicular here with the axis coming straight out like so. Okay, then what we do is we take a look at a small amount of mass. So right here is a little dm, like so. And that dm is some distance away from the axis right here, r. Essentially what we have to do is take the product of dm with r squared, and then add it all together. That then gives us the following integral. So, now notice that it sort of looks a little similar to an integral that we've already seen, specifically in Chapter 9. What integral is that? The integral for center of mass. But there are a number of differences here, as we'll see. Okay, now when talking about a center of mass integral, the product, first of all, is between the mass and the vector, the position vector r. This right here is not a vector. This is a magnitude that is being squared. In addition to that, there's no 1 over m term over here for rotational inertia, like we saw earlier for center of mass. So even though the integrals in general look very similar to each other, how they're calculated is actually quite different. Okay, now when it comes to evaluating this integral, there are specific geometries, specific distributions of mass that you have to know how to do. They are the following. So find the rotational inertia, find the value of I here for the following systems. Okay, part A and B here, there's a little bit more to it as well. But parts A and B are going to deal with the same object. They're going to deal with a one-dimensional stick. Now remember what is meant by a one-dimensional stick. That means that it has length like so, but we ignore the thickness in this direction, and we ignore the thickness in this direction. In reality, of course, this one-dimensional stick is actually a cylinder, like so, but we're going to ignore the thickness this way and ignore the thickness this way. And then part A and B are pretty similar to each other. What we're going to do first of all is have an axis of rotation that is passing through the geometrical center of the stick. So if I hold it like this and then rotate it like so, the axis of rotation is perpendicular to us, like this, it's rotating about an axis passing through the center of mass. So I want to calculate what the rotational inertia is in that situation. Then in the second situation, what we'll do is move the axis of rotation from the geometrical center and have it pass through the end point of the stick, like so. So then what I do is I take the stick and I rotate it like this, like so. When I do this in my hands, it's actually harder for me to rotate the stick like this than it is for me to rotate the stick like this. This is actually relatively easy for me to rotate. So then therefore, just based upon what I'm feeling here, and you can verify this for yourselves as well, with a stick, what I should find is that the rotational inertia here should be a bigger number than the rotational inertia here. Okay, Dave?
Is there a reason that the sigma doesn't have an upper limit?
Which, I'm sorry?
Under the point particles. Is there a reason it only has I as a lower limit?
Well, we just have, in terms of the point particles, let's say we have I particles making up our system. When I derived that expression last time in class, I thought of it as two particles. Remember I had two sticks?
Oh, so the upper limit would be, oh, so you're saying it depends on the...
So the way that I derived it, the way I thought of it last time in class is we had an I particle here, and an I particle here. This was some sort of rigid object. It was all rotating like so, remember, around the common axis of rotation. Okay? Okay, now here's then how we go about setting up parts A and B. They're actually very similar to each other, as you'll see. Stuff here. Okay, for part A of the problem, let's think of it like so. Okay, right here is the one-dimensional stick. It has mass M, it has length L, and it has a linear distribution, a linear density, excuse me, that once again is called mu, like we saw it back in chapter 9. Remember, for a one-dimensional object, that mu is mass over length, it's one-dimensional density. And then right here is the axis of rotation, so the stick will rotate like so, perhaps on my diagram. Now, when we set up this integral, we kind of build this integral in much the same way as we did for the integral still on the right-hand board there for the center of mass. What we do first is we take a look at a small amount of mass within the stick. So right here, for example, is a dm. And that dm there is some distance away from the axis of rotation. Right here, this distance, that's the value of r here in the integral. This is all just occurring along the x-axis. Let's just refer to that as x. So right off the bat here, the r is just going to be equal to x. And then we write the mass here, dm, in terms of the density, just like we did for the center of mass calculations back in chapter 9. Once again, remember that density, mu, is mass over length. So think of this infinitesimally small amount of mass here as having an infinitesimally small amount of length associated with it, dx like so. So the dm then, the mass, is equal to the density multiplied by the length. So I use the same series of steps here to arrive at building this integral here for rotational inertia, just like we saw back in chapter 9 for center of mass. And now I just plug everything in. So I is going to be the integral of r squared dm. So x squared and then times dm, which is mu times dx. And now I arrive at an integral where we integrate over the distance. So if I place the axis of rotation here in the center of the stick, what are then the limits of integration? It's from here to here. Think of the axis as the origin.
0 to L.
Not from 0 to L. Negative L over 2 to positive L over 2, like so. So, now what is the integral of x squared? 1/3 x cubed. So then therefore, when I integrate, we're going to have a 1/3 and then still mu. The mu is a constant. And then times x cubed. We integrate then between our limits like so. So I first of all plug L over 2 into the expression here, and you get L cubed over 8. 1/3 mu times L cubed over 8, and then minus. And when I plug negative L over 2 into x cubed, you get negative L cubed over 8. So minus on negative L L cubed over 8. Like so. And now we simplify. Okay, the negative signs here will cancel out, so then therefore I'm going to get 2L cubed over 8, which is just L cubed over 4. So I get 1/3 times mu times L cubed over 4. 3 times 4 is 12, and then we have mu. Mu, remember, the density, mass over length, is now thought of as the total mass divided by the total length. Let's plug that into here. So then therefore, the rotational inertia of the stick, when I rotate it through an axis that passes through the geometrical center, that's going to be the following. Do a little bit of canceling. And this 1/12 ml squared. Notice it has the basic form of mass times distance squared. It always will be. What we have here, however, is a 1/12 that comes out in front from the actual integration itself. So depending upon the mass and the length of the stick, if I rotate it like so, then because of how the matter is distributed around the axis of rotation, this rotational inertia is 1/12 ml squared. Then in part B of the problem, it's virtually the same thing, except we take the axis and move it away from the geometrical center, and instead move it to the end like so. That changes the picture only very slightly, and it will only adjust one thing in the calculation. So now in part B, let's picture then the diagram in the following way. Here's the stick like so, and then right here, passing through the end of it, that's the axis. And then it's rotating, for example, like this. The setup of the integral is identical to what I did up on the top board. It's identical, essentially, up until this step right here. The only thing that's different are the limits of integration. Now, Bo, what are the limits of integration?
0 to L.
Now it's 0 to L, that's right, because now we're going from here to here, like so. Other than that, everything else is the same. So the rotational inertia here is then going to be from 0 to L, and then I'm going to have here still mu times x squared dx, like so. Integrate the x squared again, you get 1/3 x cubed. Between 0 and L, plug the L in, it's just L cubed, plug the 0 in, it's 0. And this is then 1/3 times mu times L cubed. You still have to replace the mu here with mass over length. So then therefore, I, 1/3 times mass over length times L cubed, do a little bit of canceling, 1/3 ml squared. So which is harder to rotate? Part B, part A? Part B is this number here, 1/3, that's bigger than, where is it, this number here, 1/12. And you can literally feel that in your hand with a relatively heavy stick. Next time you have one in hand, rotate it like so, it's relatively easy to do. Rotate it like this, you can definitely feel that it's harder for you to rotate than it is. Okay? Yes, you need to know how to do each of these. And then, you also have to know how to do the following. Okay, now, here's basically part C. It's a hoop. So once again, a one-dimensional distribution of matter. So it forms a line, in this case, just arrange it into a circle. We ignore the thickness this way. We ignore the thickness this way. So it's just a one-dimensional object arranged into a circle. And then the axis of rotation is perpendicular to the plane of the hoop, and it passes through the center of mass, which, if you recall from chapter 9, is right here at the geometrical center of this circle. So the axis is like this. what we need to do is figure out the rotational inertia if I rotate it like so. So I'm rotating it about an axis like this that is perpendicular to us like that. This is once again a relatively easy calculation to do. And then in part D of the problem, instead of thinking of it as a one-dimensional object, then it's two-dimensional. It's a disk, like so. So the matter is distributed in two dimensions like this, but we ignore the thickness in the third dimension like so. And then we once again want to calculate the rotational inertia passing through the exact same axis. It's a slightly different calculation. Part D, as we'll see, is a double integral. So now here's what, first of all, part C looks like. Much of this is going to look familiar because we saw some of these steps already, just like in the stick calculations a few minutes ago, back in chapter 9 when doing center of mass calculations. Okay, so I arrange my distribution of mass in this manner: mass m, radius r, linear density mu, once again, such that the axis of rotation is right here at the origin on my diagram, right there passing through the center of mass of the hoop itself. Okay, then in order to build this integral, the first thing that we take a look at is a little dm. Right here is the little dm, and then it's some distance away here from the axis of rotation. The distance that it's away from the axis of rotation is obviously just the radius of the hoop itself. That right there is the capital R. So the little r here, that magnitude, is just the capital R. Once again, there's no vectors here like there was in the center of mass. This is just a magnitude. So finding little r in a problem such as this is obviously very easy. And then we've got dm. The dm is described in terms of the density. The density is equal to the mass over the length. The length right here is a little arc length here associated with the circle, a little ds. Does anybody remember what the arc length is equal to in terms of the radius and an angle, however? Does anybody remember what the length element is? It's rd theta. Okay, remember how that looks? We saw this back in chapter 9, for example. It looks like this. So kind of focus in on the little dm on the diagram above. What you end up with essentially something that sort of looks a little bit like a pi wedge, like so. Right here is the radius of the hoop r. Right here is the arc length associated with the hoop ds. And then right here is the angle that is subtended. Right there is the angle d theta. Remember that the angle is equal to the arc length divided by the radius. So the arc length is equal to the radius multiplied by the angle. This is called the length element in polar coordinates. Okay, so then therefore, over here is my density mu. So the mass is equal to the density times the length. It's equal to the density times the radius times the angle. Like so. So that's the second thing that I need. So I've got the two things I need. I've got little r, which is just capital R, radius of the hoop, and then I got this guy right here for the dm. And then we just plug everything in. So the rotational inertia I is going to be integral of first the little r squared, like so, times the mass, which is mu r d theta. So, make sure I get this right. Like so. Okay, now what am I integrating here, however? Am I integrating over r? No, I'm integrating over the angle. So then therefore, what are the limits of integration? 0 to pi, that's it. So, all of this stuff here, they're constants. So then therefore, this is just the integral of 0 to 2 pi d theta. And what's the integral of 0 to 2 pi d theta equal to? It's just 2 pi. So you then therefore, you end up with this. Mu, we'll change that in just a moment, times r cubed plus 2 pi. Like so. Okay, now you still need to get rid of the density. The density is the total mass divided by the total length. Total mass divided by total length. What's the total length of the circle? Circumference. 2 pi r. So, plug that into here. So I have density mass over the circumference, and then multiplied by 2 pi r cubed. Notice that the 2 pi's drop out immediately, and r cancels as well, and you end up with something that's actually pretty easy. You end up with r squared. So once again, this is one of the rotational inertias that you need to know explicitly how to derive. If you rotate it like so, about the axis passing through the center of mass, then the rotational inertia is just mr squared. Okay? Yes?
So should we always keep going until we have just a mass and a length?
Absolutely. You have to replace the density with mass over length in these calculations. Yes?
Since one of the limits of integration is 0, you don't have to do the anti-move at all.
Well, what I'm actually doing here, I may be assuming too much with regards to everybody's knowledge of calculus at this point. But what I'm doing is the following. Let's just jump back to this step here. All this junk right here, these are all constants. So just pull it all out. So my integrand here is actually just 1. So I'm integrating 1 d theta. So when you integrate 1, you just get theta. You just get this. From 0 to 2 pi. Plug the 2 pi in, plug the 0 in, boom. There's your answer. Okay? And then lastly is part D, of course, which is the 2-dimensional situation. Starting from scratch. In the 2-dimensional situation then, now we have to think of it as a sheet of material, if you will, arranged into a disk as it is said. And now we have to take a look at a little dm right here, 2-dimensionally within the disk. And right here is its distance away from the axis, still placed here at the geometrical center of the diagram like so. There's our little r. Starting point. In this case, the little r here in r squared, that's just this little r. We're going to have to integrate in this direction. It's a 2-dimensional integral in just a few moments, because of course as I move the dm around here, the value of little r is going to vary. So this just stays as it is. And then we have dm. Density. 2-dimensional density. Mass over area. Mass over area. Does anybody remember what the area element was in polar coordinates? Remember, you could say it really fast. That's the easiest way to remember it. Bailey?
RD theta.
RD theta. That's right. RD theta. That's an easy one to remember. RD theta. And remember where that comes from? Take a look at the little dm there on the diagram a little bit more carefully. Remember, it kind of looks like this. Nice and large. Right here is this pi wedge like so. That's my dA. Okay, that dA right there is just going to be length times width. Right here is the length in terms of the r direction. Right here is the width, if you will, which is ds. Can I think of this right here as being the same size as this right here? Yes, because it's infinitesimally small. Okay, then I can describe then this distance here as the little r, like so from the diagram above. And then right here is the angle subtended, d theta. Can I think of this as r and this as r equivalently?
Yes.
Yes, because dr is infinitesimally small. Okay, so then therefore, the area dA is length times width. It's dr times ds. And the ds here is described exactly the same way as I did in part C of the problem for the 1-dimensional version of this a few minutes ago. Remember that arc length over radius is equal to the angle. So the arc length is equal to the radius times the angle, like so. Plug that into here, and then the area element is RD theta. So this is the area element in full. Okay, now that I have that value of dA, just jump back up to the top here for the mass dm. The mass dm is equal to the density times the area. So it's density times r dr d theta. like so. So I now have the two things that we need. We have just a little r once again here in blue by itself, and then my dm here is this quantity here, but I am going to integrate in two directions, over the radius of the disk and all the way around the disk in terms of the angle. So it is going to be, yes, a double integral that then looks like this. So the rotational inertia I then is now going to be the following. Two integrals. First of all, a little r squared, and then times dm. Or the theta. Like so. Okay, now, this integral sign corresponds to this variable, r in this case. This is called the inner integral. Because we're integrating over r, what are the limits of integration? 0 to capital R, the radius of the disk. Okay, then this right here, the outer integral, as it's called, corresponds to this variable here. That's the angle. So we go all the way around the disk. What are the limits of integration here? 0 to pi. Okay, now, the order of integration here in this problem actually doesn't matter. Because notice that in terms of the angle, everything here is a constant. So then therefore, the outer integral is just 0 to 2 pi d theta, and that's it. So then therefore, like the circle a few minutes ago, what is the integral of 0 to 2 pi d theta? It's just 2 pi. Okay, then, I've got sigma here, which is also a constant, so let me pull it out. And then all that's left now is 0 to r, that integral, of r squared times r cubed. Here, like so. Okay, now what is the integral of r cubed? 1/4 r to the 4th. Evaluated between 0 and capital R. Plug in the capital R, and it's just capital R to the 4th, and then minus the 0 plugged in is just minus 0. So before we simplify all the constants here and all the other junk, you basically end up with, after you complete the integration, the following. Clean up this sigma a little bit. Okay. So now, therefore, the last step here to get the rotational inertia in the form that we're looking for is to get rid of the density, sigma. This is total mass divided by total area. What's the total area of the disk? Pi squared, the area of the circle. So plug that into the expression. So I is then going to be, first of all, 2 pi times sigma, which is this, like so, multiplied then by 1/4 on the 4, like so. And this cleans up now considerably for us. Okay, first of all, the pi's cancel. Here, 2 cancels here and there, and then an r squared cancels here and here. And after you clean this up a little bit, I know it's a little messy, you end up with 1/2 mr squared. So notice that all of these rotational inertias have the same basic form, mass times some sort of distance squared. What changes from situation to situation, depending on the symmetry and whatnot, is the fraction that is out in front. Now, even though you're not asked to do it necessarily for a 3-dimensional disk, which by the way is also known as a cylinder, the rotational inertia of a cylinder is the same thing. It's 1/2 mr squared. So this right here is a cylinder. Not when I rotate it like so or rotate it like so like I did earlier, but if I took the stick here and instead, let me give myself enough room to do this here at my desk, rotated it like so. The rotational inertia of this thing here is 1/2 mr squared. The only other geometry that you have to be aware of is the rotational inertia of a sphere if the axis of rotation passes through the geometrical center of the sphere. So you rotate the ball, for example, like so. The rotational inertia of a sphere is 2/5 mr squared. In order to show that, however, involves a 3-dimensional integral in spherical coordinates. Now, when it comes to individual problems, such as what you would see in homework, exams, and on the AP exam itself, usually the problems associated with rotational inertia, especially on the AP exam itself, come in the following manner. It will be in a free response problem. And they will say, okay, in part A of the problem, they will say explicitly, show that the rotational inertia of this hoop is mr squared. They will expect you to do part C of the problem here right off the bat. If you can't do that portion of the problem, however, they say what the rotational inertia is. They say it's mr squared. You would then use it for the remainder of the example, even if you couldn't quite derive it in the first portion of the problem. That's usually how they do the example problems in the AP exam itself. The first chunk of the problem is to do this. And then if you can't do that, at the very least, you could still do the remainder of the problem because they tell you what the formula is. Okay? So you'll always be given the formula in some manner when it comes to a problem, an exam problem, etc. Sometimes they will ask you to derive it. Okay? Gabe?
Are we expected to know part D for your test? Because I remember for the center of mass when we weren't expected to know that.
This one, yeah, you got to know how to do this two-dimensional integral.
Okay.
Because they may say on the AP exam, you know, show that the disk's rotational inertia is 1/2
But no center of mass double, because remember we did one with the center of mass.
Well, that just ends up being 0 because it's right at the axis. It's not at the axis. It's right at the geometrical center, which you place at the origin. They may ask you to show that. Okay, I didn't do that on my exam, but they might on the AP exam.
Okay.
Remember, the AP exam is still 6 months away, and by the way, 6 months away is just right around the corner. This is assuming that you get a little bit more calculus under your belt, so everybody will look at the problem and then go, oh, it's easy. Okay.
For the example that you show on the table, where there's like a cylinder rotating.
They will say the cylinder's rotational inertia is 1/2 mr squared. They will say, and then they'll go blah, 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 blah.
But
Do the rest of the problem.
how is that? So that basically is the same as a disc.
Yes,
But
a
isn't there
three-dimensional
like a-
cylinder, when you rotate a cylinder like this, it's basically such that this portion of it here doesn't matter, because that's perpendicular to the axis
Oh,
of rotation.
okay.
So when you rotate a two-dimensional disc, just the circle itself, and a cylinder in 3 dimensions like so, when you rotate it like that, this portion of it doesn't matter.
And it's perpendicular to the axis of rotation.
Let me rephrase that. This portion here of the mass is actually parallel to the axis of rotation.
Oh, yeah.
When I do it like this, so that doesn't matter. It's only the stuff that's this way.
So if it's parallel,
matters.
it doesn't matter. Is it because the sine theta thing?
It doesn't matter because the stuff is not rotating. The stuff in
Yeah.
this direction is not rotating about an axis that is in the same direction.
Okay, all right.
So that's why the rotational inertia of a cylinder, ultimately, just conceptually, is the same thing as that of a two-dimensional disc. Okay? Last question, then we gotta move on.
If it's a piece of an object, like what we had on the last exam, is the only thing that changes, would that just be the limits of integration?
Yeah. That's right. Okay? But for other symmetry, or for other non-symmetrical situations, this integral here, as opposed to the integral for center of mass, can actually be really difficult to do. After we take a break in just a few moments, we're going to run through 2 theorems. In each of these theorems, we're going to take, for example, a hoop like so, and instead of rotating it like this, how would you instead calculate the rotational inertia if you instead rotated it like this? Doing this integral from scratch is extremely difficult to do due to the non-symmetric distribution of mass around the axis. There's a theorem, however, called parallel axis theorem that allows us to get around that difficulty very easily. And then there is a second theorem called perpendicular axis theorem that allows us to do the following. Start with a situation where we once again rotate the hoop, say like so, with the axis like this. But then, how would you find the rotational inertia of the hoop if we instead rotated it like this, or rotated it like this, about an axis that is perpendicular to the first one? If I was going to set up the integral to find the rotational inertia of this situation, or this situation, setting up that integral from scratch, a calculation up on the top board, is really difficult to do. But there are 2 beautiful theorems that simplify the process for us considerably. We'll see those after we take a break. Hey, kids, I gotta take attendance, and there's a couple kids not here.
Maybe the typo.
It was one of those silly kids posters that was in the wrong order.
Did you do that? Did I show up?
show sometime. Yeah, that's show. Do you really want to go there? Like more than you?
Just sit back.
Absolutely really annoying.
All right, now, calculating the rotational inertia about an axis that is passing through the center of mass of a distribution of matter, as long as that distribution is symmetric about the center of mass, is actually quite easy to do. We saw a couple of examples of that a few minutes ago. Rotating the hoop, for example, about an axis passing through the center of mass like so, a two-dimensional disk, rotating the disk about an axis passing through the center of mass like so. As long as the distribution of mass is symmetrical, those calculations are generally easy to do. However, as I mentioned just prior to the break, if I move the axis for the hoop, for example, from this point here to this point here, such that the hoop would be rotating around an axis like so, setting up the integral from scratch and evaluating it to find rotational inertia is actually really difficult to do. However, there's a very simple theorem called parallel axis theorem that allows us to go from knowing one rotational inertia to another very simply. Here's how this is done. Okay, let me set up the situation in the following way. Let's say that we have a coordinate system like so. Let's say that we have some block of matter like so, and specifically I'm going to say that right here, the origin is the center of mass of this glob of matter. And let's say that we already know something ahead of time. Let's say that we already know what the rotational inertia is of the object if the axis passes through the center of mass. In other words, if the axis is like so. So we already know this from setting up an integral like some of the problems that we saw a few minutes ago. As I said, this is generally easy to do for symmetrical distributions of matter around an axis passing through the center of mass. So now what we want to do is take the axis, which so far looks like this, and then move it here instead. This new axis is parallel, however, to the old axis like so. That's why this is referred to as parallel axis theorem. So right here is the new axis. Let's call that A, and it's parallel to the old axis passing through the center of mass. Okay, now we have some distances on this diagram that are defined in the following way. The distance from the center of mass, where the old axis was, to this point right here, where the new axis is, that distance right there is referred to as h. Okay, now the new axis right here, it has a position vector associated with it. I'm not going to draw the position vector itself, because then it gets kind of messy. Instead, I'll just describe its coordinates. It has the coordinates in the x direction, call it x sub a, and it has a coordinate in the y direction, call it y sub a. Okay, then what I have to do is I have to take a look at a small infinitesimal amount of mass here within this glop. I'm actually, however, going to use the summation notation for the derivation of the parallel axis theorem. It's just a little easier to do that way. So right here, for example, is a little m sub I. Okay, now once again, that little m sub I here, with respect to the origin, has a position. That's its vector, kind of looks like that. I'm not going to draw here because then it will get really messy. Instead, we'll think of its components as coordinates. We have an x sub I like so, and a y sub I like so. Okay, now what I want to calculate is the rotational inertia as I rotate this thing, not about this point, but instead about this point. So how do I do that? Y sub I, sorry. I miswrote. Thank you. Okay, so once again, backing up. Now I want to rotate the thing about an axis passing through this point. So what I have to do is I have to sum up the mr squareds. So the r is this distance right here, because this is the new axis. So how do I describe this distance right here in terms of all of these coordinates? Well, I have to do so by using the distance formula. Remember how this is done from geometry, or wherever the hell it is that they teach you this stuff? That's the equal formula. So it's mr squared. It's m times this distance squared. Now, what is this distance here? Well, this distance here, and then when you square it, is nothing more than the following. Okay, first of all, sub I, and then times this distance squared. That's this. Like so. So take a look at that carefully. Okay, this distance here in brackets, it's a distance squared. It's this distance here squared. How do you find this distance? Difference between the x coordinates, square them, distance between the y coordinates, square them. Take the square root to get the actual distance itself, square it then for the expression of mr squared. So this right here is just the rotational inertia of this point right here, for example, about this new axis, and then I sum up over the whole thing. And that's the summation symbol. Yes?
Oh, what is the point of having the new point again?
Okay, so once again, what we're doing is we're moving the axis from this point here, passing through the center of mass, to this new axis. I want to find, for example, the rotational inertia of this hoop. Now when I rotate it like so, that's the ICM,
Okay.
and now instead like this.
Okay.
If I was going to set up the integral from this from scratch, it's a horrid mess. I want to come up with a much easier description of doing this. This is what this theorem is all about.
Okay.
I'm deriving the theorem for us. Okay, now to continue the derivation, all I have to do is just square this out and then see what I get. So what do I get? Okay, well, let's FOIL all this junk. Let's FOIL this right here. That will then give me this. Watch carefully. Like so. Let's FOIL all of this junk here. Right. So, let's take a look at that carefully. Okay, now what the hell is all of this? Well, let me just kind of group some terms together. Notice there's lots of stuff here that looks pretty similar. So first of all, I'm going to have your m sub I, and now I'm going to group together this, this. Okay. Now I'm going to look at this piece right here. Let's write like this. And next I'm going to look at this piece right here. And then lastly, I'm going to group together this stuff right here. So all I'm doing here after I FOILed is move terms around and group them all together in this manner. Just take a look at that carefully. Just make sure you understand that.
Shouldn't all of that be in bracket?
Hang on. I'm sure I got this right.
Okay. Okay.
That's good. So now what the hell is this? Very well, take a look at this. Right there. What does that look like? It's a center of mass calculation. It's specifically the numerator of the position of the center of mass calculation in the x direction. Remember that XCM from chapter 9 looked like this. This is the numerator of it. It's XCM. What is, however, XCM? It's 0 by definition because we put the center of mass in the origin. This is 0. Take a look at this guy right here. What's that? That's the numerator of the y coordinate of the center of mass, as we saw it back in chapter 9. So, it's the numerator. So it's the y-coordinate of the center of mass, which is what? 0, because we put the center of mass at the origin by definition. So those two terms are equal to 0 for that reason. Okay, so now, what is left over? Well, so far, here's what I have left over. Write it out properly. So now, what is that? Well, that right there is an mr squared. It's basically a rotational inertia. It's a rotational inertia, however, of what? Well, what is there in the parentheses? What's there in the parentheses is this distance here squared, where this distance is the distance from the center of mass. In other words, that's ICM. It's the rotational inertia if we rotated the thing about the center of mass. Theoretically, we already know this from our integral. This right here is ICM. So then therefore, the only thing that's left is the last term here. What is the last term? Well, the last term is, first of all, just the sum of the masses. There's no I subscript here in the parentheses. So what is just the sum of the masses? It's just the mass of the whole thing. Just call it M. And then what is this here? It's another distance squared. Which distance is it? That's right. It's h squared. That's parallel axis theorem. So what the hell does it say? Well, let's try this. Yeah.
Wait, so where did the m come from next to h squared? Was that?
Okay, so right here in this last step,
That's
the
just.
sum of the masses. There's no subscript I here. Just sum of the masses. It's just masses of this. Now here's how you apply it. Here's the beauty of this theorem.
Mr. Shell, like I initially asked, where did the MI came from? Is it just because that's like any point on the mass?
So this first step right here, right? Is that what you're asking?
Back to the graph, the MI.
What the MI?
This is an M sub I.
It's just any
It's
point.
a little piece of the object. That's it.
Okay. So that's why you sum it up, right?
And I'm summing it all up. Okay, let's take a look at parts A and B. We already know the answer to part A. We're going to rederive part A, however, by using the parallel axis theorem. Okay, let's take a look here at part A first. This is once again taking a look at the stick once again. Okay, now part of the problem with our stick here of mass M, length L, density mu, blah, 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 from earlier today, when the axis of rotation is passing through the geometrical center, we rotate the thing like so. Does anybody remember what the rotational inertia was? 112 ml squared. This is ICM. The reason why it's ICM is because the axis is passing through the center of mass. And now what we want to do is we want to move the axis from here to instead here, the end of the stick. So this right here is the new axis. And notice that it is parallel, hence parallel axis theorem, to the old axis. Now here's parallel axis theorem. How does this look then for this problem? Well, ICM, we know. We have to do the integral to do this. There's no way around the integral. You've got to do that to get this. That's 112 ml squared. We already know that previously. And then plus mh squared. The h is always the distance from the old axis passing through the center of mass to the new axis. In terms of the stick, what is that h equal to? That's right, it's 1/2 the length of the stick. This right here, the h is equal to L over 2. Stick it in. So I then get 1/12 ml squared plus, let's see, L over 2 quantity squared is 1/4, right? Plus 1/4 ml squared. Okay, how many 12ths is 1/4? 3 12ths plus 1/12 is 4 12ths. Squared, like so. Now this one I had derived earlier from just using the integral itself, because for a stick it's easy to do, that's why we did it. However, you could just as easily find it using parallel axis theorem. Yes?
Does it matter that U isn't given?
It doesn't matter. The mu actually doesn't matter. It doesn't really factor into a parallel axis problem because you've already done the hard work. You already used the mu, for example, to find that, and now you're just applying the theorem. Okay, now what about the last problem here, part B? Well, for part B, we go from an axis that goes like so to an axis now to the edge of the hoop like so, where we're going to rotate like this. If we were going to set up this integral from scratch, as I said, and solve for the rotational inertia in that manner, it's a horrendous integral. We don't want to do that. We instead want to use parallel axis theorem. So now in part B's problem, here's our hoop, mass M, radius R. Right here, perpendicular to the plane of the board, is the old axis passing through the center of mass. Does anybody remember from a little bit earlier today? What's this equal to? Not for the disk, this is for the hoop. This is MR squared, that's right. We already know this. So, and then what we do is we move it, that is the axis, that is, to here. And it's parallel to the old axis, like so. So what is the distance h equal to then, therefore, in the theorem? Obviously, it's just equal to radius capital R. So now the rotational inertia from parallel axis theorem is just this. So if you move the axis from here to here and then rotate the thing like this, and I can feel it in my hands. It's harder for me to rotate like so than it is for me to rotate like so. In fact, the rotational inertia here is just twice as much as the rotational inertia here. That's kind of cute. Next is what's called perpendicular axis theory. Oh, purple. I haven't used it. Purple for perpendicular. All right, now, just to think of it most simple, let's say that I have an object that is in the XY plane. Shh. And then right here, within the XY plane, is a little m sub I. And that m sub I right here is some distance away from an axis of rotation that we'll say is parallel to the z-axis. So let's say that we already know the rotational inertia of the thing about the z-axis. Now, how can you picture this? Well, just think of the hoop in the xy plane. We already know what happens when we rotate it like so, about an axis here passing through the z-axis. We can find that by integrating directly, or if necessary, by doing some combination previously of parallel axis theorem. So let's say we already know that. What we now want to do is we want to figure out what the rotational inertia is, not about the z-axis, but instead about the x-axis, which is perpendicular to the z-axis like so, or about the y-axis, which is also perpendicular to the z-axis, like so. We want to find the rotational inertia in those cases. Now, as I said, let's say that we already know what this is. Now, from the definition of rotational inertia, this is just equal to the following. Oops, I have to summarize it for some, sorry. There we go. Like so, it's just an mr squared, where the r is right here in the xy plane, and in the xy plane, this right here, and I'm going to draw this in a different color for clarity here. This right here is x sub I, and this right here is y sub I. So those are the coordinates, like so. So x sub I and y sub I, like so. In the xy plane, those guys added up squared. That then right here is the r associated with this m sub I. That's this quantity here. However, watch what happens if I split this up into three terms. Let's just say I write it like this instead. Let's just say I write it like that. Okay, it's the same thing as the purple step above. Let's just say that I write it like this. Can anybody tell me, what is this? It's another mr squared. So what is it? No, it's not a center of mass.
Center.
What is it? No, it's not the center of the universe. It's an mr squared. So what is it? It's a rotational inertia. That's right. This right here is a rotational inertia. This right here is a rotational inertia. Now look at this one. Mx squared. Right here is the x. It's a rotational inertia about which axis? Not the x-axis. The y-axis, like so. What? Take a look at this right here. That's another rotational inertia. It's an mr squared. It's an m distance squared. That's another rotational inertia. Where y sub I is right there. So it's the rotational inertia about which axis? About the x-axis, like so. That's perpendicular axis theorem. Now what the hell does it say? Let's try that.
Wait, that's it? That's the whole thing?
Yeah, that's it. Yeah, this whole thing. So what the hell does it say? Let's try that. starting to see hints in physics here now why rotational symmetry is so
Okay, so what?
why rotational symmetry is so important. This problem is one step. Maybe a little bit hard to see in the back, but it says, use the perpendicular axis theorem to find Ix and Iy if Iz for a hoop is equal to mr squared. The origin of the three-axis coordinate system passes through the center of the hoop.
Those are I's, right? Not L's.
Those are I's, yeah, sorry, yeah, those are capital I's. If they were L's, they would be something else called direction cosines, but that's a whole other story. We won't go there. All right, so what the hell is this saying, and why is it just a one-step solution? I'm going to see if anybody here can give me the answer. Here's what I mean. Okay, so here's the xy plane like so. Here's the z-axis like so. We're going to take the hoop and just place it in the xy plane like so. So here's the hoop like this. Like so. And we already know from the derivation earlier today, of course, IT is equal to mr squared as it says in the problem. So what we need to find are the two other rotational inertias, x and y. So take a look at the problem and now think in terms of symmetry. We know that this here is mr squared. What we're trying to find is rotation about the y-axis, Iy, and rotation about the x-axis, Ix. What's the answer? I'm sorry? It's 1/2 mr squared. The reason for that is because they're the same thing by symmetry. This is exactly the same as this. So if the sum of the two is mr squared and they're both the same thing, then therefore this is a 1/2 mr squared and this is a 1/2 mr squared. Very good. They're obviously the same thing. Wait, oh? I knew someone was going to go, what? Okay, Ix is equal to Iy by symmetry. Okay, so then therefore if Iz is mr squared, and Ix and Iy are the same thing, so let me just think of Ix here as Iy. So Iy plus 2, plus Iy rather is 2Iy. So then therefore Iy is equal to 1/2 mr squared. Therefore Ix is equal to 1/2 mr squared. Notice how beautiful these two theorems are, and they give you these very simple descriptions of what would otherwise be actually really awful calculations. One of the great things about, in particular, perpendicular axis theorem is it can also describe to you very crazy rotations around really strange axes very nicely. Let me give you a nice example of this before I do camera.
What happens if whatever the object isn't symmetrical? Like,
The object is not symmetrical, then the opening integral that is necessary still to do all this. Remember, in this problem, we already know this.
Yeah.
Okay? So because we already know that, the rest of the problem was easy. Okay? But you still got to know that, and that involves the integral. So ultimately, somewhere you have to do the integration to get one thing to get the process started. But after you've got that one thing by integrating in some manner, then the rest of it is relatively easy. Yes, Kate?
How can you just assume that they're symmetrical? I mean, obviously
It is
they're
symmetrical.
And they are symmetrical, but that's not good enough for physicists. Obviously.
Sure it is. Yeah, it's symmetrical.
They just assume that. And
No, they don't just assume it, just look at it, okay?
No,
If
I
wonder what,
understand
wait,
what
watch
you're
this.
saying.
If I rotate it like so,
it's literally the same thing, yes.
yes, you said the word, it literally is the same thing.
Yeah.
That means it is the same thing. You're reading too much into this, okay? It's symmetrical, they're equal to each other, it's just the geometry is the same. There's no difference, in other words, physically, between the two axes. The reason why there's no difference is because the universe is three-dimensional. There's no difference between this and no difference between that. That's literally the answer.
What if it's
Yeah.
Yeah, just off right. If it wasn't symmetrical, how would you find the IX and the IY if they weren't the same?
Okay, if it wasn't symmetrical, if I, for example,
If you get
had my thing like so, so I know the MR squared, and then I had to do something strange. Then I had to, for example, find an axis about, say, somewhere here in the middle, so the thing is rotating like so. What I would have to do is a combination of the two theorems, parallel axis and perpendicular axis, to arrive then at whatever it is that I'm looking for.
Oh.
It would be a combination of them. It has to be done in a specific order. Hey, let's take a look at a nice little general problem. This is really cute. Football fans, you're gonna like this one. Okay, this is for football fans. Initially, it's gonna look like it has nothing to do with football.
It really doesn't. A stake of mass.
There's stakes in football.
As I said, initially, it doesn't look like it has anything at all to do with football.
I felt cool there. How to do this.
Shh.
Pretty funny.
That's a 5. That's Microsoft Word's version of a 5.
What's up?
I'll draw it out for you.
Like a 0.
It's a Greek letter. You'll see me draw it like this on the board.
Oh, that's fun.
It's also a good word for words with friends.
How do you spell it?
PHI.
Oh, it's F-E-I-E.
All right, so what the hell is being described here? Well, what's being described is taking the stick, passing the axis through the center of mass. However, it says the axis is tilted at an angle phi with respect to the stick. So what that means is we're going to take the stick and we're going to rotate it like this. So the axis is still right here, like so, but we're going to rotate the thing like that. So what we need to find is the rotational inertia. And what this has to do with football, we'll get to later.
Oh, yeah.
What this has to do with football, we'll get to later.
You're right.
Okay, yeah, we never do that.
So, drawings.
Depending on whether it's spirals or.
Whoa.
Yes.
Never response. Never. I think because my no.
But in the problem, isn't it the axis that's tilted on the stick?
Hang on. Hang on. Let me get this drawn. Let me get this. Okay, so let's think of it like that. Once again, in order for you to visualize this, look at the top of the stick. Top of the stick is tracing a circle that is perpendicular to it, like so. So that's how we have to think of it, okay? Now, we already know one thing. We already know ICM, if we rotate the stick through an axis like so, that is pointing straight at us perpendicular to the board. Let's think of that as the z-axis for the perpendicular axis theorem. So on my diagram, the z-axis is pointing straight out at us. And what is this rotational inertia? 112. So then therefore, let's think of this right here as the x-axis, and this right here as the y-axis, where the z-axis is pointing out at us like this. And by the way, I do have the directions correct here. Remember, I hat cross j hat is k hat, like so. So right there is the z-axis like this.
Wait,
so that's right in terms of its description. I've got x and y.
Yeah, if you like.
By the way, I am
Okay, now, think in terms of symmetry once again. What does the angle phi have to be such that Ix and Iy are the same? Now, before you answer that, what am I talking about here? Well, first of all, right here is Iz, 1/12 ml squared. And then this right here, as we're initially picturing it, is I which axis? It's I which? It's Iy. So right here is Iy. Now what the hell is Ix? Ix is this. Right here, where the circle of the edge of the stick is like that. Perpendicular to you, like so. You have to be able to think here about this. I'm relying on your intellect in this description. Right here is Iy. Right here is Ix. What is the angle? Yeah, go ahead, Gabe.
It's the circles it traces out, right?
That's right. So just look at the edge of the stick if you're having trouble picturing.
Oh, yeah.
Makes sense. So for Iy, the top of the stick is tracing a circle that is like this. For Ix, this edge of the stick is tracing a circle facing you is like that. Okay, now at what angle phi on my diagram is Iy, Ix going to be the same? Obviously a 45-degree angle.
How is that obvious?
Remember tree. Now, how is that obvious? At a 45-degree angle, is there any difference between this, Iy, and this, Ix? No, it's the exact same thing, just with the stick rotated 90 degrees. If I take the stick and rotate it like so at a 45-degree angle, okay, and then I rotate the stick like so, it's the x-axis, it's like a 45-degree angle. It's the same rotation.
Yeah, imagine we picked up Sherlock and he was just sideways.
Yeah.
That's right. You have to imagine me sideways. My head's that way, my leg's that way. Okay? I'm holding the thing like this, and then somebody picks me up. No, don't do it. Somebody picks me up and holds me sideways, and then you see the same stick doing that.
That makes sense. How that has to do with the problem?
funny.
Okay, so Ix and Iy are the same thing when phi is 45. Okay? Okay, now, trigonometry. What's so important about the 45-degree angle? What is the same about a 45-degree angle? Sine and cosine of a 45-degree angle are the same thing. So then, therefore, keeping that in mind, what's the answer?
What's the question?
What is Ix plus Iy?
1/24.
Keeping in mind that at a 45-degree angle,
Oh.
cosine and sine are the same.
1/24 ml.
Cosine of 45 is the same as sine of 45. What then does this have to be equal to? This plus this to be that.
Well, each one has to be equal to 1/24.
Now, don't think in terms of numbers.
Uh-oh.
Think in terms of symmetry. Think in terms of trig. What is the answer?
Sine.
Something is
45 degrees. Something to do.
45 degrees.
Weird.
Cosine squared of 5 plus sine squared
Oh my god.
All times what?
times something?
All times what?
Oh, times ml squared. That's ml squared. Oh, 112.
112 ml squared.
112 ml squared.
No, 112 m.
Bailey, you're the hero.
Oh, because it's one.
Oh, because it's one, goddammit.
That's right, yes, he's along with the curse word as well. Yes, he's not cursing at this point in physics. But it's cursing not because you're pissed off, but because you're excited.
Yeah.
So we have here at a 45-degree angle, cosine squared of 45 and sine squared of 45 is the same thing. Sine squared plus cosine squared is equal to 1. Now the question is, however, is which one is which? I just wrote down the identity that everybody knows. Cosine squared plus sine squared is equal to 1. But which one is this? Is this Ix or Iy? Well, look at how I defined the angle phi. If the angle phi is 0, then the stick is like this. What is the rotational inertia of the stick if it's one-dimensional and it's rotating like so?
1/2.
No, it's 0, because remember it has no thickness this way.
Oh.
It has no thickness this way. So if I'm rotating it like so around a phi equal to 0, then the rotational inertia is equal to 0. So then therefore, is it cosine squared of 0 that's 0, or sine squared of 0 that's 0?
Sine squared of 0.
Sine of 0 is 0. Sine squared is equal to 0. So then therefore, that's the I sub y is the sine squared term, like so, if I rotate it like that. Now think if the phi, instead of being equal to 0, was instead 90 degrees. So if the phi was 90, then it looks like this, like so. So then therefore, if the phi is 90 degrees, then sine of 90 is 1, cosine of 90 is 0, then the rotational inertia around the y-axis would be 1/12 ml squared, as it should be. So in other words, the sine squared term is in fact the rotation around y. This is the rotation around x. Very good, Bailey. Very good. It's a little tricky, however, as you just discovered here. It's a little tricky to figure out which one is which. The easiest way to figure out which one is which in this calculation is just think, okay, what happens if phi is 0 and if phi is 90, depending on how it's defined on the diagram. That will then tell you which one is which, as I just went through. Now, what the hell does this have to do with football, or with anything for that matter? Well, let's say, take a football. How many of you have played football before? Okay, some of you have to some extent in some manner, okay? Everybody says, well, you gotta take the football, and you gotta throw the football with a nice tight spiral like so. You don't wanna throw it such that it wobbles in this manner as it rotates, or wobbles in this manner as it rotates. The reason for that is because when you throw a football, you want the rotational inertia after it leaves your hand to be the biggest number it can possibly be. The reason why is because it then becomes very hard for the wind resistance, or gravity, to exert a torque on it to then start to cause it to wobble in some manner. In other words, give it some sort of angular acceleration. So you want the rotational inertia to be as large as you possibly can. So now picture the football like this. Do you want the football to rotate like so, or rotate like so?
No.
No, because then it'll be the 1/12 cosine squared, or equivalently the 1/12 sine squared. Remember that a trig number is always less than 1. So in other words, one of these guys, the Ix, for example, just by itself, just this term right here, if the football was wobbling, that's a smaller number than if the football was not wobbling, but was instead of rotating like this around the z-axis as I defined it. That's this guy right here. So you want the rotational inertia when you let go of the ball to be as big as it can possibly be, because then it's hard to torque it in some manner. If it wobbles in some manner, then it's easy to torque it. The reason why is because the rotational inertia is one of the trig terms, the cosine squared or the sine squared, which is less than this number here. That's good enough for that.
A little bit.
All right, take a look here at the board. So in addition to the web assign, by the way, sorry to do this to you, these 3 problems here from the book are pretty cute. These guys here are to be done by hand. They will be due, however, just next Friday, not on Monday. Next Friday, good enough. Make a note of it, 10, problem 40, 54, 83, and 100.
Those are by hand?
Okay, yeah, so those are by hand, okay?
Okay.
No, they're not. So this is the theory, that's perfect. Now, when the final, yes,
Oh, yeah, yeah.
what is my way
Can I take a picture of your planner?
host of
I crossed it, I just left. What is?
Hey, you gotta work your way through it.
What if you said? Oh, I don't know.
You gotta work yourself through this mental.
To be honest, I don't.
And
Even
the axis,
though they probably went to some. Taylor, did you get that?
Yeah, turn it off.
Did you get them?